Hello everyone, welcome back to Let's Unbound. So we are in final episode of this particular playlist and we are in AP Precalculus Exponential and Logarithmic Functions, which is Unit 2. So yes, in this episode you can expect an exam style problem solving of the whole unit. So most of the skills are covered in single question and also it will be helpful for you like how to answer the questions in free response section, right? So this will have calculator parts and also without calculator part. So yes, here we are into the lesson. So a scientist is studying the growth of bacterial culture. The population in thousands of bacteria after T hours is modeled by the function P of T is 500 times e power 0.12t where T greater than or equal to 0. Part A, growth and interpretation. Interpret the meaning of 500 in context of this problem. Find the continuous growth rate as percentage. And part B, predicting and solving. Estimate the population after 10 hours and then after how many hours will the population reach 200,000 in 1000, 2000 in 1000, which is 2 million bacteria. Then part C, inverse function. Find the inverse T of P, which gives the time in terms of population. Interpret T of P in this context. Then part D, transformation graphical analysis. The scientist defines a new function Q of T is ln P of T. Simplify Q of T, state the domain and range, discuss the key features between Q of T and P of T, and write down your implications. And last part, application of logarithmic scales. Suppose another culture is measured on a logarithmic scale for population base 10. Explain how using a logarithmic scale would make interpreting long-term growth easier. Right. So this is all about the one free response questions that we are going to discuss in this video. And let's get into solution part. So it is a growth function and yes, exponential growth. P of T is hours and P of T is on particular time, what is the population? And yes, T greater than or equal to 0, it's a basic thing, right? Time will be greater than or equal to 0. So let's solve the first part. Interpret the meaning of 500 in this context. So 500 times an exponential function, right? So this 500 will represent initial population, right? So 500 here represent the initial population of the bacterial colony. So here 500 represents initial population of the bacteria. And so how can I say, I can also say like this, there are 500 bacteria, 500,000, right? So I'm writing 500k bacteria at when time t equal to 0. This way also you can interpret. And find the continuous growth rate as percent. Continuous growth rate is e power kt, means this k will represent the rate of growth or rate of decay, right? So, which is 0.12. They're asking in percentage, it's multiply 100. That's it. So it's 12% is the continuous growth rate and 12%, we can say 12% per what, like per second or something. We have to relate it with the context here. So T is in hours, right? So we should say 12% per hour. This is a rate. Continuous growth rate as percentage, right? So that's simple, part A. Now, part B, predicting and solving. Estimate the population after 10 hours. So the equation we know directly, P of T is 500 times e power 0.12 t. After 10 hours, so you plug in 10. T equal to 10, that's it. So P of 10 is 500 times e power 0.12 times 10. Right? So we can directly go to the calculator and solve this. So what is your function? You just name it as, don't use P of T or something. Just go with f of x. is equal to e power 0.12x. Right, so this is, and we need f of 10. That's it. So you can directly plug in f of 10. And we got 3. Oh, I forgot something. Or is that 500 initial population, right? So 500 times. And we got this. F of 10 is 1660.05 something. So let's interpret our answer to the whiteboard. Yeah. So we got this f of 10, I mean p of 10 in this context, right? Equal to 1660.05. So 3 significance only they will be asking, right, in our exam. So we can just make it a whole number here, as the whole number is having 4 digits. So we can do that. And approximately. So approximately 1660. Your population is always in thousands. So we have to multiply it by 1000, right? So when you're interpreting the answer, the population after 10 hours would be, if you multiply this with 1000, as your P of t is in thousands, so you will get 166, 2 zeros, 2 zeros. So you got 1,660,000 something. So I can approximately say it's 1.66 million. Right? So this way you can interpret your answer so that whoever like not a math people will understand, right? So that is how your interpretation should be, right? And let's move to the next part. So B part, predicting and solving. After how many hours will the population? So the reverse rule, right? So P of t we know. P of t is 500 e power 0.12t, but I need hours now, and I know the population, 2 million bacteria. So if you plug in 2 times 10 power 6, it's wrong. Your population will be in thousands. So you should divide the 2 million by 1000. So directly if you plug in 2 million, it will be wrong. So it's 2 million in thousands means, so 2 into 10 power 6 divided by 1000 means 10 power 3. So you just do 2 times 10 power 3, which is 2000 is what you should plug in. Right? 2000 equal to 500 into e equals 0.12t. I need to solve for t. So the important part is here. Right? And let's simplify 2000 by 500 equal to e power 0.12t. And you simplify this 20 by its 4, e power 0.12t. And how will you solve this further? I want t to be the value, right? So taking ln on both sides, ln 4 is ln e power 0.12t. Ln 4 is, like if your ln has its input, and if that input has exponent, you can take that in front, right? So 0.12t, ln e. Ln e is what? It's just 1. Because ln e is log with base e, and if log b is 1, right? Same base and same input. So in that case, it will become 1. So we got ln 4 by 0.12 equal to t. And yes, we can approximate it again using calculator. This is a very simpler part, so I'm giving it to you. Right? Use your calculator and find this. What is t? So we will get approximately 11.55 hours. Right? So unit is important. So after approximately 11.55 hours, bacteria population will reach 2 million. Right? So you can write that statement. And this is fine. So when they ask to interpret, instead writing 11.55, right? So 50.55 hours you convert to minutes. It will be 0.5 is 30 minutes, right? So it's approximately 33 minutes. Right? So you can multiply by 6. So you can say 11, how many hours, how many minutes. That would be the best interpretation, right? Not like decimal hours. Right, into the part C, inverse function. Find the inverse function t of p, which gives times in terms of, which gives time in terms of population. So actual is population in terms of t. But if you do inverse, like the variables will get exchanged. It will give you a function. When you give population, you will get the time, right? So that is, and we need to interpret here. Okay, so let's start with our P of t. P of t is 500 times e power 0.12t. Okay, so you can do, like, how will we do inverse? We will exchange the things and all, right? So now I'm just using P for easiness. So P by 500 equal to e power 0.12t. Then you take ln on both sides. Ln P by 500 equal to 0.12t. Okay? And then we need t. So t equal to ln P by 500 divided by 0.12. So this is your T of P. Your T is independent, P is dependent. P is dependent, T is independent. And equal to ln P by 500 divided by 0.12. This is T of P. So now we did the first part. Okay. And interpret T of P in the context. So whenever you find inverse, so like 2, your P should be greater than or equal to 0. Right? Because greater than or equal to 500. Right? Because we know initial population is 500. So that is in case P is greater than or equal to 500 and your T will be greater than or equal to 0. Right? That is the condition you should give. So like domain and range condition. And interpret T of P in the context. What is T of P? T of P is time in hours. Time in hours. Like required for bacteria to reach the population P. Bacterial population to reach P thousands, right? It's not just P thousands. That's it. This is the interpretation. Like this is your second part, right? And we are moving to D. Transformation and graphical analysis. The scientist defines a new function. Q of t is ln P of t. So basically, they are taking ln, right? They are taking, it's a semi-log plot, right? This transformation is. So let's see. Q of t is ln of P of t is what? 500 e power 0.12t. And taking ln means it's ln 500 plus ln e power 0.12t. Ln 500 is ln 500. You can approximate if you want. Ln e power 0.12t is 0.12t. Ln e, they are reciprocals, like they are inverses. So Q of t after, like this new function is linear function, right? So if this is y and this is a constant like c and this is m, this is x. So y equal to mx plus c format is what we can observe here, right? And now state the domain and range is the next part, right? State the domain and range of Q of t. Q of t is ln 500 plus e power 0.12t. Domain is what? Like domain is what are the possible values of t, and we know that t is greater than or equal to 0 for sure. T cannot be negative in this context. So its domain is, and t greater than or equal to 0 in this notation 0 to infinity. And Q of t will be a population which is greater than or equal to ln 500 because I know very well this is going to be greater than 0. Right? So Q of t will be greater than or equal to ln 500. So your range would be from ln 500 to infinity. Right? And this way you can stop. Like you can mention or you can approximate. If you approximate, you will get something like 6.215 to infinity. This is the range. Right? And moving to next part. Discuss the key features of Q of t and P of t and write your implications. So key features in the sense, maybe let's to P of t. P of t, like you can just visualize the graph e power, because it's very simple. So we don't want to go with calculator actually. It's a growth function, and 500 is initial population, means when x is 0, like y-intercept is that 500. And it will be a growth function like this, right? So P of t is an exponential growth function, and its y-intercept you can mention, right? Then it's increasing, constant up. Those are the key features. So P of t is equal to, so P of t is exponential function. Exponential function, we know that you can mention about the growth. So exponential growth curve. And also it's increasing concave. Right? Then y-intercept is 0, 500. Now, so let's see q of t now. Like one of the key features of your exponential function is intercept, right? Like, sorry, horizontal asymptote. So y equal to 0, mathematically, y equal to 0 is horizontal asymptote, right? So y equal to 0 means here P of t is horizontal asymptote. Why? Because as x, like your t tends to negative infinity, P of t tends to 0, right? But contextually, when we speak, it starts from here only. So we are not taking this part, right? It starts from here only. So, but contextually, t tend to not infinity, negative infinity is not applicable. So asymptote will not be the part of real life context. Asymptote won't be the part of this context. So don't just ignore. Just you have to key features, asymptote is main, and you should say mathematically is this, and in this context, why it isn't, we are not considering, right? So next is let's do q of t, the new function, which is ln of p of t, and we already solved it, right? So the ln 500 plus 0.12 t, it's a linear function, and its slope is positive, so it's increasing in nature. So here concavity will not hold. Increasing in nature. And what else? We can say y-intercept again. So y-intercept is like 0, ln 500, right? And then it's starting and extending to the right side. So we just mentioned that. And no asymptotes for this, right? So now, what is your implication on this? So taking a ln, actually you take a ln and the exponential get into linearization. So this is what happened in semi-log plot. So you take ln means we are partly doing log and partly linear. So the semi-log plot linearize the exponential group. Linearize the exponential group. This is your implication, and simple implication I have given. Now, part E, application of logarithmic scales. Suppose another culture is measured on a logarithmic scale for population based in. Explain how using a logarithmic scale would make interpreting long-term growth easier. So yes, the main aim of the semi-log plot is this, logarithmic scale is this, right? So when your P of t is this, 500 e power 0.1 t, and once you take ln on both sides, so ln P of t equal to, we got the Q of t, right? You can just write that, right? You will get ln, okay, log with base 10 they're asking. So let me take log with base 10. Or simply you can mention log. Log P of t is log 500 plus log e power 0.12 t. Ln would be easier, but still, that's okay. So this will be your, like I will be making because I want to work on this, right? So let me use the change of base rule. So ln p of t, the base is 10. Ln 10 equal to ln 500 by ln 10 equal to ln e power 0.1 t by ln e. I just applied base of rule. I changed the base to exponential base. So ln 10. So ln 10 will get cancelled and you will get ln p of t is ln 500 or not equal, it's plus 0.12 t. So this is semi-log plot. Your your independent is t and your dependent variable is ln. So vertical axis will be ln and your horizontal axis will be lead. So this is a semi-log plot. And yes, for higher values like 2 million bacteria, all those stuff, it is easy to visualize here and you will get, actually it's exponential, but here you will get a straight line if you graph this particular semi-log plot, right? And yeah, so why it is easier? So on a linear scale, exponential growth will be something like this. So both are linear, it's like P of t and t. So for higher values, like if you're doing a long-term behavior, there is a quick increase. So it's hard to compare over long periods, but in logarithmic scale, multiplicative changes. So here it's everything is multiplied, but here it's additive. Additive is something we can manage even for higher, longer term growth, right? So that's why you can say this. The population axis transforms in ln p of t like multiplicative to additive changes. So that changes the exponential to linearization, which uh, helpful to look the trend, right? Even in when the population is higher, right? So that's the basic aim of logarithmic scales too, right? And with this, we are at the end. So thank you so much for joining. We will be posting a new playlist on very soon, which is trigonometric functions, right? So stay tuned with us. If you have any doubts, queries, suggestions, you can drop them in comment section. Keep learning and let's meet in next playlist. Until then, stay curious.